design parameters. We are coming from 2 at the beginning. And you see that thanks to these 5 design parameters, we can try to optimize the things differently. But again, and we are coming back to what we said at the beginning, if you want to optimize this, you are not optimizing the TSFC. And if you want to optimize the TSFC, you are not optimizing this. I have said you at the beginning with this curve, that was this one, with this curve, that if you optimize towards this direction, you will never optimize to this one. And if you optimize there, you will not optimize to this one. This is a truth that we said from the beginning, and we still observe here, even if we have increased the design parameters, hoping that we would be better, we have a bit decreased the differences, but we are still staying with these 2 different missions, acceleration capability or cruise, subsonic cruise, supersonic cruise. All of them are related with the TSFC. Okay? Of course, we can go into the details. We can certainly also discuss lambda CA. I've not discussed that here in the afterburning chamber. So you have lambda CA. Is it lower, higher than in the turbojet? These are things that we can certainly discuss. What time is it, please? Okay, so before ending this class on afterburning engines, there is something that we need to discuss. Let's say not into the details, but at least to give you a flavor of something that is important in mixed turbofan engines, and also in turbojet engines. I'm coming back to the exhaust nozzle. The exhaust nozzle, we have always, we have discussed yesterday the importance of the length. This is longer if you have afterburning. Turbojet or turbofan, you will have a very long exhaust nozzle. The length of the nozzle is about 50% of the length of the whole engine. So you are multiplying the length of the engine by a factor 2 because you have afterburning, roughly speaking. But there is something else that we have not discussed. We have always said, okay, I can have this situation in an exhaust nozzle. And I was reaching the situation where in the section 5 here, that was the exit area, that I could have an adapted nozzle, and an adapted nozzle, it means that P5 is equal to PA, and M5 is lower than 1. And in the choke nozzle, I have that P5 is larger than PA, and that M5 is equal to 1. Okay? Now, the situation is, we have explained that this is the best case. This is the case where you can optimize, let's say, the thrust. And so, you want to have an adapted nozzle. Problem. When you put afterburning here, okay, m dot Fa, burning, and here you have TT4'A. One of the objectives of doing that, in order to keep it simple, this is with the objective of flying supersonically. In order to fly supersonically, most probably you need afterburning, and so afterburning will be used to fly supersonically. What is the consequence of that? If you increase the Mach number of the flight, what will be the direct consequence? There will be a direct consequence at the level of PT4. And PT4 will do what? PT4 will increase. Why? PT4, this is coming from PT3, coming from PT2, coming from PT1, etc., etc. And if you increase the Mach number, PTA is increasing, PT1 is increasing, PT2 is increasing, everything is increasing. And so you will increase PT4. Is it a problem? Yes, because what makes that my nozzle is choked or not choked, this is the ratio PT4 divided by PA. And if, due to my supersonic flight, I am increasing PT4, I am increasing my nozzle pressure ratio for a constant altitude. And if I'm increasing my nozzle pressure ratio, what is the consequence? Maybe, most probably, I will come with a choke nozzle. And the choke nozzle is reducing my thrust. My thrust is reduced, but I want it to accelerate. And so you see that you are going into the opposite direction of you would like to do. You want to fly fast. Because you fly fast, you are increasing your Mach number. Due to that, you increase PT4, you increase the nozzle pressure ratio, and you opt to have an adapted nozzle, and you go to a choke nozzle, your thrust decrease, and you want it to fly fast, but you have less thrust. So it's not in the good direction. So what can you do? You will be, let's say, in order to keep it simple, you will be with always Mach 5 is equal to 1. This is not what you want. And how can you then save the situation? How can you re-improve the situation? There is only one way. In order to re-improve the situation, you need to put a divergent ear, because you will have a diverging supersonic nozzle, a diverging supersonic nozzle, and in a diverging supersonic nozzle, what will you have? You will have that the Mach number will increase, but the static pressure will decrease. And you see, we were with P5 larger than PA, and thanks to the supersonic nozzle, you can come again with P. Let's call that exit, because we don't know exactly now what is P5 and so on. You should speak about P throat here. P exit, that is now the new P5, can now become equal to PA. And you see why people are putting convergent, divergent nozzles on aircraft engines. And especially when using afterburning, especially when you have a turbojet with afterburning, and maybe even more a turbofan with afterburning, which is even more flexible, where you will even more often go to subsonic, supersonic, subsonic, supersonic, because this engine is much more flexible than the turbojet with afterburning. And so on a turbofan with afterburning, the ideal solution is to have a convergent, divergent nozzle, because this nozzle is again adapted. You have an adapted convergent divergent nozzle with, of course, now M5 that is not anymore lower than 1, and 5 is now higher than 1. So a convergent, a purely convergent nozzle, when adapted, is subsonic, and a convergent divergent nozzle, when adapted, is supersonic. Okay? Very important to note. And of course, at that time, you have a nozzle that has a throat, and this nozzle has an A5, that is this one. This is this one that you should call A5. Okay? And at that time, you see that thanks to this, you can optimize your thrust. Then you would say, yes, but why is not everybody doing that? Because it looks like so obvious what you are explaining. Indeed, but this nozzle is not as ideal as what we would like, as we would think first when you are looking at the explanation I have given. Why? Because everything is depending on PT4 divided by PA, that I have called the nozzle pressure ratio. But also everything is depending now on P5, P throat, larger than PA, and the PA I have here outside. Okay? And PA will change with the altitude. Okay? And so, let's consider, for example, that you are flying at a given Mach number. Let's say Mach 2. You have, at that moment, a certain P throat here that is valid for the flight altitude and for the Mach number you have. And let's say that with the same engine, you fly at another speed and with another altitude. This will change, but also this will change. PA will change and P throat will change. And not in the same ratio, P throat divided by PA will not be equal to a constant. And so, if you have a certain length here, with a certain angle here, what will happen, depending on the change you have had in P throat due to the speed and the altitude, and the change you have had in PA due to the altitude, what will happen, the pressure here, P5, will become lower or higher than P8. Yes? Because you have constructed the system so that you decrease in a supersonic flow the P throat from 1.2, 1.3, 1.4 PA down to PA.